Industrial Engineering and Management from the Karlsruhe Institute of Technology. During his master's degree, he also studied at the Shanghai Jiao Tong University, broadening his expertise in the field of new energy systems. Sam Abdel Rahman, system architect, residential solar and energy storage, received PhDs in power electronics from the University of Central Florida in 2007. He joined Infineon Technologies in 2011 and is currently responsible for developing the application roadmap of server and data center switch mode power supplies and renewables. Sam has experience in the power and semiconductor industries with a focus on system architecture, topologies, and control. Following the presentation, we'll have a live Q&A with Jonathan and Sam. You can submit questions at any time during the session using the chat box on the right of your screen. We will also provide attendees with a PDF version of the presentation near the end of the session, and you will be able to find this under the Handouts tab. Thank you so much for joining. With that, I'll hand it off to Jonathan and Sam for the presentation.
So hello and welcome everyone for today's webinar on how Infineon's wide bandgap semiconductors enable the next generation of solar PV and energy storage solutions. My name is Jonathan Schmidt. I'm the Global Application Manager for Solar Residential and Energy Storage, and with me today is Sam Abdel Rahman, System Architect for Residential Solar and ESS. This is the table of content today. Let's jump right into it. First, we start with the trends and market dynamics. So you see in the headline, the success story of residential solar and energy storage continues. On this chart, you see especially the growth story for residential energy storage. In the recent years, we saw a huge jump and a huge adoption rate of the energy storage. And if I click once more, you see here also the growth story of residential solar. Both is highly attached to each other. So we see in the years 21, 22, 23, this enormous growth story. And we also see that this is further continuing till 2030 and beyond. We see this especially in all the different regions, EMEA, Americas, and APAC, but especially in EMEA, but also in the US, we see a higher attach rate right now of these residential systems with each other. In the future, we see more and more integration. So I already was hinting into it. Residential solar is getting installed more with energy storage. And I will also further explain, we see more and more systems also being installed with EV charging, and there's further kind of integration to be expected. On this slide, I will explain you which kind of integration we see and which kind of installations we have in the residential ecosystem. You already see on the top the first kind of installation, which is a microinverter. So here we come directly, or the microinverters are directly behind the PV panels. First, we have here the DC-DC stage and then the inverter stage in one device after the panel, and have then directly an AC, which is then being fed to the grid or to the house. The next kind of installation is a hybrid setup or even a normal string inverter. So where I have the string inverter at my house. Here, of course, you see I have this boost stage and PPT stage in this inverter. I have then the inverter stage, and even I can couple this to a DC coupled energy storage if I have this hybrid setup. A further option is that I have this power optimizers together with string inverters being installed. Power optimizers are additionally being installed behind every panel, and they have, similar to microinverters, different function. For example, the rapid shutdown in case of any emergency. They can higher the yield of the whole installation, so efficiency boost. And of course, it's a really nice function in terms of monitoring your whole system. Another option is, of course, AC coupled energy storage, which you can install if, for example, there's already a solar system string inverter being installed. Then an add-on would then be, of course, an AC coupled energy storage. Here, of course, if you see the whole system, we have more power conversion stages, but definitely can be here an add-on with solar or even without. And last but not least, I was already hinting to it. We see the V2G, so vehicle to house, vehicle to grid, EV charging installations that can be, of course, standalone, but also being further integrated in such kind of solutions. Let's come to the next slide where I explain you what are the current trends for solar and for energy storage. Let's start with solar. Here we clearly see that the system and the panels become more and more powerful. In the past, we started with 300 watt panels, even lower, and then we're further to continuing to go higher. Now I put here higher 400 watt. I think this will even go higher for residential installations. Also, we can observe higher PV string voltages here around 600 volt. In general, we can make a comment about warranty, 25 years. This is especially a case for power optimizer, microinverter installations, the string inverters, energy storage, but also we see here a high kind of warranty, which has a direct impact also to the components being used, of course. Lower system cost, so the whole system of the string inverter is, of course, getting cheaper over time. Now in the recent months, just to give one example, we see especially on the PV panels some kind of price pressure that the prices are dropping further and further. Looking to the right-hand side on the energy storage trends, clearly we see this hybrid solutions coming up more and more, solar plus energy storage, all-in-one solutions, solar plus ESS plus EV charging. Higher energy capacity and power. This is counting for the installed batteries, which can be seen in all the regions. Again, especially Europe and US, like the EMEA region. And of course, higher voltages for the battery, where we have in the past predominantly low voltage batteries, and these are now transitioning further to higher voltage batteries even. So what does that result in the wide bandgap offerings, and which kind of system benefits we can see here? Definitely we see with higher switching frequency, this allows to reduce now the system cost by reducing, for example, the size then. In general, with our wide bandgap products, silicon carbide, gallium nitride, we can reach higher efficiencies for this solar and energy storage solutions. In general, a statement, we have reduced losses and heat dissipation, which allows for higher power and more integration. And last but not least, enabled bidirectional operation for charging, discharging the batteries. Yeah, I will give further examples where we see this materials, wide bandgap materials, then exactly being used in the system. Coming to this slide. Examples of wide bandgap adoption in the residential ecosystem. Here I want to give you a brief picture of where it is already used by today. The first example, V2X solution, EV charging, energy storage. So this is an all-in-one solution. Specifically here, I want to hint to Omron, a Japanese manufacturer of this system, which has really a light and small version now in the market. This is being achieved by the adoption of gallium nitride. In general, you see the two inverters in the middle, that we have a silicon version. And then, of course, this is the size comparison, which you could theoretically also reach with a GaN or silicon carbide. High adoption rate on the microinverters of gallium nitride. Here we definitely will see on the high voltage side or on the secondary side of the microinverters, we see this adoption. This is coming soon, I think, for multiple players globally. On the bottom left, the string inverters here, we want to give you a general guidance. This is now high power string inverters. In the past, I had really bulky, big installations being installed with silicon. Then some more modern installations. We could even shrink the size. And finally, with the use of silicon carbide, which you can clearly see, we have a huge weight reduction, but even with a power increase of earlier this 100 kilowatt, now we see this 225, and then just at 77 kilogram. Now I'll give you some further examples. The portable power stations getting more and more adoption all over the world, also because gas or diesel generators sometimes even getting banned. So this is a common solution. GaN here is already being adopted. Power optimizers and microinverters in general, we see here GaN or even a combination of silicon plus GaN being in the market. These are just some examples where it can be used. Definitely the picture about all the solutions in the market is looking a little bit different. Therefore, I want to hint to my next slide. So we expand here strategically to maintain our position as market leader. Here I want to give you a brief picture about all these different technologies: silicon, silicon carbide, gallium nitride. This is our technology view for the year 2030 for residential solar and energy storage. The left bar, which you see here, higher than 600 volt, you see rather a split of one third of silicon, SiC-MOS, and GaN. Where is this coming from? The GaN is definitely being used in, for example, microinverter installations, some string inverter installations, partly, of course, also in the energy storage. Just to give you some examples, the silicon carbide, we see definitely a value add in the energy storage installations, in maybe even three-phase microinverter installations designs, where this is further driving adoption. And then, of course, silicon will be still widespread in the market, as it shows really good characteristics, and we can design high efficient systems even with silicon. So all of this will be there on the high voltage side. Now looking a bit more into the lower voltage side of gallium nitride, 40 to of outer wide bandgap materials, 40 to 200 volt. What we can see here that we expect in the future, especially gallium nitride coming further in, but let's say on the broader scale will still be with silicon solutions. So what we're going to do to support you with all of these technologies, let's first highlight what is Infineon doing on the silicon side. Here we have major investments into Dresden and Villach, our two front-end manufacturing sites. In Dresden, we had here investment for up to 5 billion euro for this planned 300 millimeter module to really ramp up the capacity. And the same is already happening in Villach, where we have a large-scale capacity ramp up continuing to happen to serve our customers with this kind of technology. Looking into wide bandgap, and here we have really exciting news because Infineon is definitely committed to serve these technologies. We have more than 2 billion of an investment in further front-end capacity. We're building currently one of the largest silicon carbide fabs in the world in Kulim, but also we see here further investments in Villach in Austria. And also to hint to the gallium nitride side, Infineon's GaN capacity is increasing significantly until 2030 to really support volume growth at customer. We expect that this technology will come and we are ready then to further ramp with our customers that we already get these volumes being served. Really exciting news is also the successful acquisition of GaN Systems in 2023. And as you then can see also with this pie chart at the bottom, so with this platform or combined technology platform, we're really featuring the leading GaN IP in the market. And we have the strongest R&D force to really speed up time to market for our customers. You see this here with this one example, the number of patents where we have a leading role in our industry. Coming now to my last slide, with Infineon's one-stop shop for residential solar ecosystem. Definitely we have a commitment on the silicon carbide and gallium nitride side of our switches, and this is also the main focus. But I also want to highlight that Infineon is committed for this application, and therefore we offer a whole ecosystem of solutions to even go beyond the switches. So first of all, you see that we have the right gate driver solutions. We are further investing to have the right controller solutions with our XMC and PSOC families. We see that a requirement for the residential ecosystem is a communication where we can use Bluetooth, Wi-Fi, and other solutions. And here we definitely have some exciting products for you. Also with our new isophase family, we see the 4 and 2 channel digital isolators coming on the market. And last but not least, I also want to hint to the BMS side, because every energy storage we see attached to the power conversion, also the battery management system. Here we have the right switches, the battery management ICs, authentication solutions, current sensing solutions. So we try here really to address the whole portfolio to make this transition happen and to support our customers as good as we can. Okay, this was the short introduction in the trends and market dynamics. At this point, I want to hand over to my colleague Sam Abdelrahman. He will further highlight wide bandgap in solar and energy storage topologies. Thank you.
Thank you, Jonathan. So in this section, we'll go a bit more on the technical side, talking about wide bandgap, how it can be applied and provide some benefit in some solar and energy storage topology. So to start with, I picked maybe 3 of the main characteristics of GaN and silicon carbide compared also to silicon. So on the left, we see a plot of the RDS on with temperature, right? Or this shows the temperature coefficient of the technology. As we see, it's in GaN and in silicon, as temperature goes up, the RDS on goes up. We see the bottom line where silicon carbide is, it has the minimum RDS on rise. So this is a clear benefit for silicon carbide and make it the perfect device for a higher power and efficiency application. In the middle, we see the QSS. So GaN and silicon carbide have clear advantage over silicon, over QSS. So QSS is basically the charge stored in the output capacitance of the switch. And the lower, where you can have a smaller dead time and easier ZVS or zero voltage switching. And this is very important to enable the higher frequency applications. And also on the right side, this is a gate charge profile. So a smaller gate drain and total gate charge also enable the soft switching and the higher frequency. And this is a very important in even some of the lower power and microinverters, where the advantage go to higher switching frequency in hundreds of kilohertz, maybe up to megahertz. And this is a view of the 2 main architecture, like what Jonathan showed at the beginning. The main 2 architecture connecting a PV system to an energy storage or a battery can be AC coupled or DC coupled. AC coupled is basically the battery go to a conversion stage, which is a bidirectional DC to DC, and then an inverter, and connected directly to the grid or to the AC point. In the hybrid inverter, we connect the battery to the DC bus between the 2 stages in the string or the PV system. And if you look at the green boxes, which are labeled bidirectional DC to DC, these are can be CLLC, dual active bridge, or non-isolated boost converter. And the pink or the purple boxes, inverter, these are DC to AC, Here I put 3 examples of what's commonly we see, which are H4 and HERIC and ANPC. The common feature of all these topologies that they are bidirectional, because at the end they connect to a battery. So they have to provide a bidirectional flow, and the devices has to run in an active switch and a rectification mode as well. So, and that is the main topic of why wide bandgap provide a clear value, whether silicon carbide or GaN, because they have a very low QRR or even no body diode in there. So, and I think this is, I will, in the next slides, I will give details on one by one example where GaN or silicon carbide provide the technical performance or density benefit. So let's start with this example here. So this is a CLLC. So CLLC is, as you see, it's an isolated resonant topology. It can be run in different modes. It can be below resonant frequency or above resonant frequency. So this condition, which I label as discharge. So on the left, I have a battery that's fully charged, and then it's discharging to the bus that's eventually go to the inverter, to the grid. So in this mode, I'm running into in the above resonant area, and the device on the secondary side will be a high voltage device and will be running as a synchronous rectification. Therefore, the reverse recovery of the switch is very important. As you see in the simulation where I put the dot there, the device will turn off at a current that is not zero. And that current is basically, when you turn off the switch, will go through the body diode. And then when you turn on the primary switch, that diode current will be hard commutated, and you will lose energy or losses due to the reverse recovery. So if you see on the table on the bottom left, we see a simple comparison that's normalized. So CoolMOS 7, this is a fast diode version. So this is the what we say the 100%, or what we normalize against. CoolGaN has or GaN has no body diode and no reverse recovery at all. So it completely eliminates this hard commutation or reverse recovery loss. And even CoolSec, it has 5x smaller, or 20% what a silicon carbide, or a silicon MOSFET has. So in conclusion, GaN and silicon carbide are very enabling for bidirectional switch that can be run, or bidirectional flow that can be running into synchronous rectification or active. And in this next slide, here we have the opposite flow. So we are charging the battery, and we are working below resonant frequency. And in here, the device or the high voltage side is running as an active switch. And what we see, the dot I pointed on the simulation curve, is basically showing the current that is at the turn off. So the device will turn off at some turn off current. It's not zero, and there we have losses. So having a faster switching or faster turn off device mean that you have a lower energy loss at the turn off. And one of the parameters that determines this turn off speed is a QGD. And here we see in the two tables comparison I put there between CoolMOS and CoolSec, you have almost a factor of 4. If we see the QGD, 24 nanosecond nanocolumns compared to 6 nanocolumn for CoolSec. And then when we go also in CLLC, like I said, CLLC is a resonant topology. and going to higher switcher frequency and with the ZVS, one of the optimization is to optimize the dead time. So QSS or a higher QSS leads to a higher ZVS or a longer ZVS dead time, and that means higher RMS current and higher conduction loss. So the right side calculation or plot actually illustrate what's the effect of or the relation between dead time and RMS. This y-axis is an RMS factor. So here I calculate what is this factor or additional RMS I get if I increase dead time or frequency. So for example, where you have the X, where 400 nanosecond and 500 kilohertz operation, this tells you that the RMS will be almost 20% higher compared to an ideal sinusoidal waveform, right? And any dead time you introduce between the positive and half sinusoidal cycle make the current discontinuous, and that's how you increase RMS. So this is what, for a better or a lower RMS and therefore conduction losses, you want to be as an ideal sinusoidal or very low dead time. And the table here shows how QSS compare between CoolMOS 7 and CoolGaN and CoolSiC. So almost 13% for a CoolGaN compared to the CoolMOS or a silicon device. Another famous topology is DAB, dual active bridge. So dual active bridge is not a frequency modulated like CLLC. It's a phase shifted. So we phase shift the primary side from the secondary side. And if we look at these waveform, key waveforms, the last one on the bottom, we can see that the devices will run at ZVS. Of course, there are different modulation method or variation of this topology. But basically, the primary and secondary can have a ZVS turn on, but they have a hard turn off. And again, the same story we put for the LLC. QGD and QRR are very important parameter when you turn off a synchronous rectification or an active switch at the current that's not zero. So QGD will give you lower turn off losses or E off, and QRR will give you lower QRR or reverse recovery losses. And in all of these applications, when the device run as a rectifier, usually we run it like what we see on the right side as a synchronous rectification mode, where we turn on the gate. We don't pass a current through the body diode, but still, I think the requirement is you need to be robust and be able to withstand higher surge current in some abnormal condition. And this is what this comparison is doing. Basically, we pass a 10 millisecond or a half cycle high current through a device from source to drain when the gate is on, as on the right side, and the gate is off, as in the left side. And we make sure that the device survive. And CoolSiC definitely is robust and rated for high commutation and high surge current. Now, LLC, CLLC, and DAB, and even buck boost are for the DC to DC bidirectional. Now I want to move to the inverter side. So here I put, I think, two examples. The first one is for the Herrick inverter. I think this is a very common topology derived from, or a variation of the H4 to solve the common mode noise. So we have the center leg, which is back-to-back, devices, as you see here, S5 and S6. So these behave as a rectifier switch or a freewheeling path. If the idea here is all these switches, S1 through S6, can be as IGBTs and run at lower switching frequencies. Or you can do a hybrid between S1 to S4 being active switches running at higher switching frequency. You can replace them with CoolSec and gain some efficiency. And also S5 and S6 can go to CoolSec and take advantage of the lower conduction losses or lower RDS on. So the idea is IGBT to CoolSec or silicon to CoolSec in this topology can provide lower conduction and switching losses and even higher frequency. So here's a simulation that I've done in Plex for these for two same design using an IGBT device or a simulation module, and also a silicon carbide device in the bottom. So this is a 6 kilowatt. Input is 400 volts. Output is 230 AC. The message is, as we see, that the 6 device total losses in the silicon IGBT was 78. In the silicon carbide is reduced by 12%. And that's even though I think the key is not in this particular design, wasn't aiming to save losses, but to run at almost 3x the switching frequency. So instead of running 16 kilohertz in the IGBT, silicon carbide was increased to 50 kilohertz. And that has a clear advantage on the passives and the magnetic size and volume and the power density. And then the next topology I like to show also is multi-level ANPC. So the circuit is shown an example of a 3-level ANPC. So ANPC can be also modulated different ways, like S1 to S4 and S5 to S6 can be all high frequency legs, or S1 to S4 can be in this case, we make it lower frequency, and S5 and S6 are the high frequency. So one of the characteristic, or this topology has a split cap. So with an input of 400 or 500 volts bus, S1 and S2 only sees half the bus. And also S5 and S6 also will be seeing half the bus. So this enables the use of lower voltage rating devices. And S5 and S6 being the high frequency devices, now we have an opportunity for a 400 volts CoolSec. So it has a lower switching losses and on-state resistance compared to 650 volts, and also offering an attractive price position. And here we have, this is something coming in a quarter or, very soon, portfolio of 400 volts CoolSec devices ranging from almost 11 to 42 milliohm in these two SMD packages, D2 pack, 7-pin, and TO leaders. And this is an example, also simulation in Plex, where ANPC was compared with the HERIC. So with ANPC being a split bus, it's usually done in a split phase configuration. So you see there are 2 legs of ANPC. 2 of them is 3 kilowatt. The output to the grid is 2 ACs in series. So 115 plus 115 gives you the 230. or you can support 115 in some regions like US or Japan. So the main value proposition here is, if you look at the bottom table, I can run Highline, Herrick, and ANPC and almost have the same losses. But if I apply the ANPC split phase at the low line, I have much lower, or almost 3x lower losses at the low line. And this is one of the benefits of a split phase. A split phase, of course, can be done with different kind of topologies, ANPC, NPC2, and others. But here the ANPC is a clear, new topology that we think that will take advantage of 400 volt silicon carbide devices. And next, I like to move to microinverters. So microinverters, we see on the right and left two architectures. So the left is a voltage source. Basically, this is a two-stage architecture. The panel goes through a DC to DC to a DC bus, 400 volts typically, and then go to the inverter, to the grid. And then the current source, basically, we can name this as a single stage. So the panel go to a DC to DC that output a rectified sinusoidal. And then the unfolding is just a low frequency circuit to unfold the rectified sine. So the unfolding is not considered as a stage. So here are some drawing of common topology or example topologies of both architectures. And I labeled where you can use cool-GaN. So when we talk about H4 inverter, like what we see on the left side, so H4 inverter, we typically have a slow leg and a fast leg. And the fast leg, both devices will be, one is active and the other rectifier, and depends on the grid polarity during the operation. But with any half bridge topology or hard switching, reverse recovery is very important to reduce losses and noises. And here we see that cool-GaN has zero reverse recovery compared to silicon. On the right side, one of the main trending topology is a single stage cyclo converter. So this applies back-to-back devices to be able to block positive and negative grid voltage polarity. And usually these microinverter and cyclo converter aim to run at a higher switching frequency and soft switching, and cool-GaN can provide this low QSS and low QG compared to silicon, as we see in this table. So yeah, GaN in cyclo converter in particular can offer a very good value and enable much higher switcher frequency. So speaking about the cyclo converter, this is even an additional value proposition for GaN. So GaN can be monolithically bidirectionally switch, or you can monolithically integrate two devices back to back. So what we see in just below the topology is just how we transition from discrete switches. So to end up with the same RDS on, we need 4 devices of 140 milliohm, for example. With a monolithic integration, you can end up with a single 140 milliohm device. Because this merged drain provide you the most effective die utilization and to the same equivalent RDS on. This is a clear benefit of how GaN or monolithic integrated GaN or bidirectional GaN can enable new topologies where back-to-back devices or switches are needed, clearly for this example of microinverter. Another microinverter application is multi-level or multi-PV panel, where you have 4 or 8 panels, and generally they could be a single phase or a 3-phase. In an example of, or in a case of a 3-phase, for example, if I have line to line 400 or 480 volts, the bus has to be in the range of 800 to 900 volts. And then the inverter stage, where we see Q9 to Q15, have to be 1200 volts silicon carbide, or 1200 volts devices, right? And there where silicon carbide provide, a clear option for efficient and robust device, especially also with the hard commutation and the low QRR. And MV GaN, medium voltage GaN, which we refer to as MV GaN is anything 400 volts or below. So solar optimizers are these small circuits or small modules that we place on the backside of a PV panel to maximize its power generation or harvesting. And these optimizers can be typically these 2 circuits you see, like just a simple buck or a 4-switch buck boost. Both are hard switching, and they run into like 100 or 200 or so switch kilohertz. They can process single panel or multi-panel. So here are some example of power. You could go up to 600 watt in a single panel, or up to 1.3 kilowatt or so. So where GaN plays a role here, these topologies are hard switching. So it's always reverse recovery is a problem, especially if you go to higher switching frequency. So you can use GaN with no reverse recovery and increase switching frequency and reduce the inductor size and passives and even thermal dissipation. So of course we offer GaN and medium voltage GaN. Here at the bottom we have what we call IPS or GaN, or integrated power stage, where the GaN could be integrated with a driver, or a half bridge integrated with a driver for easy to use and more power density. We are now developing at Infineon a modular reference design, a platform for a hybrid inverter. So this will address small and residential and small commercial systems that can go 6 to kilowatts. So the main blocks, like you see in this bottom left diagram or block diagram, we have a PV DC to DC, and then DC to AC inverter, but also we have the DC to DC battery charger and discharger. So these 3 main topologies, like shown on the right, of course, they all have the gate drivers cards and controller cards, connectivity cards, sensing circuits. So the idea of this project is to have everything modular, where you can plug and play different circuits to enable customers to fast evaluation of our devices in these topologies, and eventually reuse these solutions in the PV and ESS systems. And this is the last slide, which is summary and key takeaways. So going from the top right plot, we go clockwise. So like Jonathan started saying, I think it's obvious the energy storage and the PV inverter or solar application and installation have been growing and continue to grow. And for that, Infineon is in the right position to catch that growth and supply the needed capacity. And especially, we see the growth of these devices or these products or this application with wide bandgap. So that's where we have this major investment in wide bandgap and technology and capacity and IP and R&D as well. And of course, we look at the system as a whole. So Infineon is a one-stop shop. Like Jonathan already presented, we have all the ingredient of a solar or ESS system, all the components that we can offer. And from a technical side, of course, I tried to show in my section that wide bandgap has the right figure of merits to fulfill the trends of higher power and higher density. We can go to higher switching frequency to reduce system cost and BOM cost. We can reduce losses and heat dissipation to go to higher power. CoolGaN has a clear benefit when it comes to the bidirectional monolithic switch and enable a new topology like the cyclo microinverter. CoolSiC body diode robustness. CoolSiC is very positioned to be used in this bidirectional flow and a buck boost battery device to charge and discharge the batteries. And that's the last slide. Thank you for your time and attention.
Thank you so much to Jonathan and Sam for that great presentation. Lots of good information. We've already gotten some audience questions, but there's still time to submit more if you haven't already. Do that on the right-hand side of your screen. But why don't we take a look at the ones we have? I think this is probably for Sam, but Jonathan, if you want to jump in, please feel free. Are SMD packages thermally capable, and why would someone choose SMD?
Yeah, thank you. A very, very good question. And we always get this question